Yes, welcome to the YouTube video lecture series. Today we are going to do chapter number 17, which is current and resistance. In fact, this is the the electricity, current electricity portion. You remember you finished before chapter number 15, electrostatic, the charges at rest. Now we are going to study the charges in motion. Once the charges are moving, we say electric current is flowing. The topics we'll be discussing: electric current, Ohm's law, resistance and resistivity, and electrical energy and power. And in fact, this concept, the current electricity, it's really a significant and a foundation for electrical measures. You know that. And we will discuss here what are the factors on which the resistance of a material, of a wire depends, like dimensions mean length, diameter, etc. Right. Let's start the first topic, electric current. The current is the rate at which the charge flows through a surface, some certain cross-sectional area of a wire, for example, through that wire for some time, delta t, for example. So the charges, current is equal to charges that are flowing over the time duration. So if you look at the charges, the unit of charge is coulomb per second. This is called ampere. So the SI unit of current is ampere. As I told you, 1 ampere is equal to 1 coulomb per second. Right. You know, before the discovery of the electrons, the scientists, they believed that the direction of the current flow is the flow of the positive charges from the positive terminal to the negative terminal of the battery. We call it traditional or conventional current direction. Even after the discovery of the the electrons, still the scientists, in honor to the old scientists, they are still using the conventional current direction. But keep in mind that electronic current is opposite to the conventional current direction. This is the conventional from positive to the negative terminal, and this is the flow of the charges, electrons, sorry. So, in common conductors such as copper, which is the good conductor which normally we use, the current is due to the motion of the negatively charged electrons. But keep in mind that the charge carrier can be positive or the negative charge. In metals, the charge carriers are the electrons. Right. So how many charges are, sometimes you need to calculate how many charges, number of charges you have to find out how many charges, the number of charges flowing through certain cross-sectional area of the conductor, of the wire, for example, which is, if I say, if n is the number of the charges or the electrons, for example, and charge on one particle or on the one electron, for example, which you know that 1.6 times 10 to minus 19 coulomb, right? And we know that current is equal to charge over time. So the charge can be written as this one. Now, this is the total charge. How much? This is the total charge, which is equal to the N multiplied by Q. N is the number of the charges, for example 100, 300, 500, whatever, and Q is the charge on one electron. So this is the rule you can find out. N will be equal to, from this equation, N will be equal to I delta Q over small q. Q is the charge on one electron. Okay, so this is what I have already written here. Okay, so from here, as I told you, this is equal to I, which is average current, time over Q. Q is the charge on one electron, I is average is the current flowing through the circuit or the conductor, this is the time duration, this is the number of electrons, number of the charges, this one. Okay, this is how you can calculate. Let's go to one example to use our knowledge what we just finished. Yes, example 17.1, please. Right. So charge on one electron will be given to you. If not given, not given here because we are using the book and you can use the table for the constant values, but it's given to you. Okay. This one given. So the amount of charge that passes through the filament of a certain light bulb, in this is delta T, this is delta Q. A part, find the average current. So the average current we just finished, that flow of charges in time delta T. 1.67 coulomb. Okay, divided by time 2. You would get your answer 0.835 ampere. This is your average current. B part, you have to find out the total number of charges, okay, the number of electrons that pass through the filament. So as we just finished in the previous slide, that N is equal to I current multiplied by delta T over Q. Q is given to you 1.6 10 to minus 19. Average current you just found out, and time 2 seconds. So you would get total number of electrons 2.61 10 raised to power 19 electrons. Okay, total number of charges, total number of electrons passing through this circuit in the given time 2 seconds. All right. Next is Ohm's law. Yes. You know, Ohm's law is really very important rule in current electricity. So this is how my students, they remember this rule: V is equal to I multiplied by R, where V is the potential difference, I is the current, R is the resistance. Okay. Experiments show that for many materials, including most metals, the resistance R remains constant over a wide range of applied voltages or the current. So voltage is directly proportional to the current. Okay, so voltage V and the current I. I write V is equal to R multiplied by I. R is the constant, as I told you that it remains constant over a wide range of temperature. So R is equal to V over I. So V in volts over current ampere ohm. Okay, so the unit is ohm. We use this Greek letter ohm. Okay, so ohm is the unit for resistance. Now, if you draw the graph, this is how you can remember if V is equal to I multiplied by R. If you need I is equal to V divided by R. If you need R is equal to V divided by I, like this one. Okay, so this is how you can remember this rule. All right. If you draw the graph between voltage and the current, you get a straight line, inclined straight line. This shows that the graph is linear. Okay, so graph is linear between voltage and current. Okay, so del V over del I will give you a constant slope of the graph, by the way, which is the resistance in the unit of ohms. Right. You might have, R is the resistance, as I told you. You might have seen in the labs different types of resistors. This is the carbon resistor. We can have its resistance value with the color coding, and this is the symbol for the resistor. This is the wire wound variable resistors, also called the rheostat. If I slide it, I can have any type of any value for any circuit, so I can fix it here. So this is the variable resistor, and this is a funny cartoon for this is the voltage. V is equal to I. This is the current multiplied by R. Okay, this is the rule. So what happens actually? This resistance in the unit of ohm, it's in fact it's trying to stop the current or reduce the current through any current. So you see this is tightening it, this cartoon, whose name is ohm, or the resistance in fact, and the voltage of the battery, it's pushing the charges to move through the conductor. This is how someone posted it on the internet. This is very good, the cartoon for that. Some devices, they don't obey the Ohm's law. Obey means that the graph is not linear. In fact, it's like this one. So we call them non-ohmic materials. The materials which obey the Ohm's law, we call them ohmic materials. things, and the ones who don't obey, whose graph is not linear, it is non-linear graph, like example of this non-ohmic device is diode. So once you draw the graph between the voltage and the current on this side, okay, so you get like this one, not a straight line. So in that case, resistance is not constant, it changes with the the temperature. Right, this is like this one. Now the resistivity. Resistivity is the characteristic of metals, of materials. The scientists already, they have tested, experimented, and they found out for every metal, for every material, the resistivity. You see, the resistance R is directly proportional to the length. If you have a longer wire, resistance will be larger value, and also it's inversely proportional to area, cross-sectional area A, which is equal to pi r square. If r is the radius, this is the area, but if you have this r, the radius of that wire, cross-sectional area, you can find out pi r square. So if we combine these two, I would write L over A. If I write some constant here, this one, R L over A. So this is Greek letter. It's constant, as I told you, we call it electrical resistivity. So electrical resistivity, I can write from this equation, R, I take this to the other side, and L here. The unit for this, ohm, area, meter square over meter. So the unit is ohm meter. The SI unit for resistivity is ohm meter. Right. You might have done experiment in the lab about to find out the resistivity, and you might have found the resistivity of copper and brass wires and compare with the actual and the real values. Real values, we have this table, for example. If you look, silver, copper, okay, silver has the smallest value for the resistance, then copper, then gold, aluminium, tungsten, and so on. We normally use copper because it's cheaper than silver, and it has good, small value of resistivity mean higher value for the conductivity. So it allows good amount of current to pass through those copper wires. Let's go to this example 17.3. Yes, yes, please. You have resistivity 1.5 times 10 minus 6 ohm meter. It will be given to you, not given because you are given table in the book, but in the exam it will be given, of course. It's a constant value. Calculate the resistance per unit length. So resistance per unit length you have to find out. Okay. Now we have this rule we just finished. You need resistance per unit length. I take this length over here, and you are left with the rho, which is resistivity over area. Area, you have to find out pi r square. R is given to you, right? Pi r, 0.321 millimeter. Keep in mind, convert it into meter. So you get the area 3.24, this one. Okay, so area 3.24, and the resistivity will be given to you. So finally you get resistance per unit length 4.6, and with the unit ohm per meter. B part of the question, you get the point? Calculate the resistance per unit length. This one you have to find out. Okay, so you have this rule where R is the resistance, L is the length of the conductor, this is the resistivity, okay, and A is the cross-sectional area. Okay, right. So this is your final answer. Now B part of the question, you have to find out the current. If the potential difference is 10 volts, maintained across a 1 meter length of nickel wire, it's a conductor, what is the current in the wire? So current you have to find out. So we have Ohm's law, V is equal to I R. So we can find out I is equal to V over V is 10 and R is 4.6. Okay, 4.6. So you get the current value 2.12 here. Okay, right. You know, this is the resistance per length, 4.6 ohm per meter. You need R. So R you will get 4.6 ohm meter over meter. So 4.6 to be used here. Okay, this is for the second part. You get the point? Resistance per unit length, 4.6 ohm per meter, but you need resistance. So multiply here, which is 1 meter, so you get 4.6. Okay, right. So that's all. So this is end of today's lecture, and we will do the remaining topics, electrical energy and power, and one more example in next lecture, just after this. So you can link the remaining part of this chapter with the second part of this chapter. So thank you very much and see you.